So yeah, thanks a lot, Sylvain and Charlotte, for the invitation. I'm going to present to you. I'm going to try to present to you a consistent overview of my research activities from the last 4 years, approximately. So it's mostly centered about the works of two of my PhD students. You will see their names pop up several times during the presentation. It's a bit of an experimental presentation. I've merged different bits of presentation, so if sometimes it seems a little bit far-fetched or something does not work, please bear with me. We'll move on to something that might be more your speed just a little bit later. Just to be sure, how many times do I?
So you have
45 minutes.
Yeah, 45 minutes to let time for question.
Okay, so what I'm wanting to talk about today is generative models, and especially why I think generative models are a promising avenue for remote sensing. And the main point that I have to bring up is the difference between generative models and discriminative models. So as far as I've seen in the program, most presentations will be on discriminative models. So models that try to predict the value of some random variable y based on the observations of a random variable x, which is nice. That's the way most people do it. So we're focusing on the conditional distribution of y knowing x. But there's one question that discriminative models cannot answer is what does a typical observation look like for a given class? So let's say you are trying to do land cover classification, and what does a typical building in your dataset look like? Well, you cannot really know that based on discriminative models, because discriminative models, they don't give you any estimate of the probability of X, the observation. And I modified the slide this morning, so of course, something is screwed up. But for generative models, we do the opposite, which is we are trying to estimate the data distribution for a known variable y, which is illustrated in that figure. So basically, in generative models, so generative models covers a lot of more different things than generative AI or whatever. It's not only image generation. But typically, the things that we want to do with generative models is we estimate what observations X are typical or in most cases are more likely, because generative models are trained to optimize the likelihood of the observations that are generated. But they can do a lot more than image synthesis. So pretty much any one of you, I think, know that you can use fine-tune stable diffusion on whatever dataset that you have and generate new remote sensing images. But to be frank, I don't really care about that because I don't see the value of generating new images when we already have so many real acquisitions. But if you take it in the opposite direction, if you have a real image, you can project it into the latent space of your generative model and try to answer the question, what is the likelihood of this observation in the latent space, given, for example, some kind of metadata, some kind of conditional variable that you have conditioned your generative model on. So let's say if you do what is the likelihood of this specific image over Paris in June, you can do anomaly detection because you assign a likelihood score to this image in a given context. And if the likelihood is small, but you know that this image is real, then maybe this image is unusual, or at least it's unlikely for some characteristic in the dataset. But you can also condition on classes, which is the typical way of basically using Bayes rule to do classification with generative models, which is to say, what's the likelihood of this image representing a river? And if you do that for any classes that you want, so what is the likelihood of this image representing artificial terrain, of this image representing a snowy mountain, then you can take the class with the maximum likelihood and it gives you a classifier for free. So, okay, that's a basic theory on generative models. That's what I teach my students, basically, when I tell them about generative models. So why would you be interested in generative models for research? I think there are three main reasons to dive into generative models for Earth observation. The first one is the opportunity. You have large-scale image generators and data generators, LLM, vision language models, diffusion models, and so on that are available, and already several groups have done the hard work of fine-tuning those models on remote sensing and Earth observation data. So if you want to use CLIP, you can, for Earth observation, use remote CLIP. If you want to use stable diffusion, but you work on Earth observation, you can use diffusion SAT, and so on. So that's one reason. Okay, you have the opportunity to work with large generative models, so why not use them? The other reason, I think, is the pragmatic side of things. Generative models, in contrast to discriminative models, you have this need for labels, for supervision. But generative models, they can just be trained to estimate the distribution of the data, so you just need data, which is a little bit easier to get than annotated data. And if you want to condition models on let's say time, date, sensor characteristics, those are metadata that are readily available in Earth observation. So you don't need more to train generative models than basically the data that you can get from Copernicus, from IGN, from any agency that you like. And the last reason, which is the most compelling to me, is that it gives you a strategical interest in positioning your research a little bit off the side, by working not on predicting something, but on modeling the data distribution, which is a way sometimes to make it easier to do uncertainty quantification, to give a likelihood estimate, and if you're a little bit careful, you can also, because you are modeling the data distribution, add some prior assumptions about what the data might look like. So integrate physical priors and so on. So it opens up, I think, avenues that are difficult to investigate with predictive models by just switching from one type of model to the other. So this is the overview of the talk. Basically, I will give you an overview of the different things that we did with my PhD students and collaborators on using generative models for remote sensing. You'll see that it covers much more than image generation, and I will basically never speak about image generation after the third part, which will cover work that I did not do. So just to give you a bit of history, in the prehistory, so 8 years ago, large image generators were basically science fiction. They did not exist. The main breakthrough was a big GAN, which scaled up GAN training at the ImageNet level. And it allowed Brock and colleagues to generate images that were significantly better quality than what existed before. And after that, it was really, just getting the ball rolling, adding text in control GAN, going higher resolution using VQ GAN, which used basically latent space modeling in the latent space of a variational autoencoder. Then the one that you probably all know, stable diffusion, which switched from the oldies, which were generative adversarial networks and VAE, to the diffusion models that are now the state of the art, but more on that later. And then just scaling up things with stable diffusion 3, which is trained on Lion 5B, and so 5 billions of image and caption pairs. With so not diffusion models, but flow matching, which is, as you will see, something that is quite similar to diffusion models. And the applications are not constrained to image generation. If you keep only one thing from my presentation, it's that. I want you to understand that you can do so much more than synthesizing new images with generating models. So of course, you can generate models and you can generate images and edit existing images. That's already very helpful. For example, if you want to do simulation of what would Paris look like in 2050 when the temperature will have increased by 5 degrees. But you can also do a lot of inverse problems, which is something that we're often facing in remote sensing. So if you want to remove the clouds, you are doing in-painting or gap filling. If you want to denoise your data because you have atmospheric noise, if you want to do super resolution, and as I've said at the beginning, you can also turn your generative models into classifiers. Especially something that I find very interesting is to use generative models as a way to perform anomaly detection. And I'm going to say a few words about flow matching, which is the main class of generative models that we are using with my PhD students. It's kind of state of the art, but the state of the art is fluctuating a lot. So I'm going to present flow matching and hide some of the nitty-gritty details under the rug. And if you have more questions at the end, I will be able to point you towards some resources because it's a huge jungle, the literature on flow matching. But I want to give you a sense of basically how those models work. So the core idea of flow matching is that you want to match two distributions by learning the velocity field between them. And I say the velocity field, but it's actually a velocity field because they could be different, but we're going to do assumptions. So mathematically, this means that we have an operator that's the time-dependent flow, which maps a time between 0 and 1 and your data distribution from a distribution P0 to a distribution P1. And basically, you are saying that, okay, this transformation, if I take the derivative across time of that operator, phi, well, it's guided by a velocity that's ut, that depends on t. And this gives you a velocity field that you can plot, which is how do you move the mass of your distribution at each point across time. And if you want to move from one point at t equals 0 to t equals 1, you have to integrate along this velocity to follow the trajectory and move one point to the target distribution. All right, so that's the basics. Of course, it does not say anything about how we can train models in this setup. So to train a model in this setup, what we do is that we say, okay, we don't know the velocity, but we are going to approximate it with a neural network. So we have to choose a definition, an analytical expression of the velocity. And in most cases, which is the linear interpolance framework, what we are saying is that, well, the interpolation is a simple linear interpolation. So the point at zt is simply the weighted interpolation between z0 and z1. And I'm going to say later how we choose the pairs z0 and z1, but just take it as we have 2 points, one in the source distribution, one in the target distribution, and we're linearly interpolating between the two. So the velocity is just the difference between z1 and z0. So it's a straight vector. And we are just training a model to say, okay, if I'm at this position in the field, and I'm at a specific time t, then the velocity that I need to predict is the difference z1 minus z0. So this gives a very simple regression objective to train a model. So to make that more useful than simple generation, we have to add a few things. In classical flow matching, we are defining a generation setup, which means that our initial source distribution is Gaussian in the space of the dimensionality of the data. And because we don't do any specific assumption on the source and target distribution, we sample the pairs Z0 and Z1 randomly and uniformly across all possible pairs. So that's what we call an independent coupling, because if we don't know how to pair one observation from the source distribution to one observation of the target distribution, then we just sample across all pairs, and we hope that by averaging the velocities, it's going to work out, which it does in practice. So in the generation setups, this means that we are mapping Gaussian distribution to the data distribution. And then if you want to get a new observation, you can just sample from the Gaussian, you integrate across the velocity field, and it gives you a new observation, which is fine, but that's a little bit limited because, as I've said, I don't want to just generate new images because we have enough images. In my case, most of the time, I want to bridge two data distributions. I have the target distribution and I have a source distribution. I have pairs of images. If you take super resolution, for example, or SAR to optical image translation, we have images that are the source, and we want to transport those source images into specific target images. So in that case, we're not randomly sampling the pairs. We assume that we have pairs in the dataset, which is quite easy to do for us in Earth observation because the data that we have is geolocalized. So we can have pairs that represent the same geographical area, but taken, for example, at different times or at different under different modalities, or before and after a specific event, and so on. So we are using this data-dependent coupling based on, I'm just going to sample what are the natural pairs, so the pairs of images that cover the same area in my datasets. And instead of giving you just generation, this gives you conditional generation, so image-to-image generation, basically. So what can we do with that? So I evacuate the obvious topic, which is generating new images. As I've mentioned, DiffusionSat is, as far as I know, the first mainstream big diffusion models for remote sensing. It does the job. It's trained on both caption and metadata. And similar applications, similar methods have been introduced in EcoMapper to fine-tune stable diffusion and do image generation conditioned on environmental variables, such as temperature, humidity, and so on, to do climate simulation and projection. So what would a specific part of the world look like in different ecosystem variables? That's a fine line of research that's just not mine. So I'm not going to talk too much about it. One thing that I like, though, is synthetic data augmentation, where you generate data conditioned on basically the semantic labels that you would like, but that are difficult to annotate or to obtain in the real world. This is something that I've done with Perla Dubinsky, which was a former PhD student, but on object counting and not for remote sensing. And it's very effective when you don't have a lot of data, a lot of annotated data for a specific task. Well, generating the data that you don't have can be a way to do data augmentation. And colleagues from the LASTIG lab have a paper on using diffusion models to create change detection pairs. Because as you probably know, if you worked on change detection, it's really hard to annotate change detection pairs because changes are not that common in Earth observation dataset. And the definition of what a change is can be a little bit tricky to have a consensus on. So that's for image generation. And as I told you, that's not the main topic of the talk. And now we're going to dive into more specific types of applications of generative models. And one that I especially like is inverse problems in remote sensing. So inverse problems are very common. And the one I started with was super resolution. So in deep super resolution, you want to train a deep model to retrieve a high resolution image from a low resolution image. And you have a degradation between the high resolution image and the low resolution image. So you assume that the low resolution version was obtained by applying a degradation operator on the high resolution observation that you have. Of course, it's not invertible, but we try to invert it as best as we can. So as a flow matching problems, we can formulate that as P0 or source distribution is the dataset of low resolution images, and P1, the target distribution, is the dataset of high resolution images. Compared to classical computer vision, in classical computer vision, you can easily simulate low resolution version of your images just by downsampling. In Earth observation, in most times, the HR and LR images are acquired by different sensors, because if we had the high resolution sensor, we wouldn't need super resolution in the first place. And as you can see, there's often time gaps between the images. So you can see that the radiometric properties have changed between the Sentinel-2 image and the Spot6 images, despite them being at, I think, 48 hours of time difference. And you can see if you zoom that, sure, the image on the right is has more resolution, but it's also not exactly the same properties because these are not the same sensors. So 2 years ago, 3 years ago even, when Amy Okabayashi, which is a PhD student, I'm co-supervising with plenty of people, including Charlotte, Nicolas Corti, and Thomas Corpetti. We investigated super resolution with different kinds of models, including generative models, and there are quite a strong baselines. GANs, diffusion models, are strong baselines for super resolution, but one tiny little problem that downstream users don't like is that you can invent non-existent details. And this is in a large part due to the time gap between the high resolution and low resolution images. Most of the images that we use are taken from low cloud coverage. So in the summer in France, those are from the Brittany region. And in the summer, there's something that's occurring is that basically the crops are cropped. And well, the appearance change. So the model sometimes learns to, just predict a crop which is a different state than what's in the low resolution image. And this is typically the kind of thing that we can observe. It's your low resolution image and your super resolution version have different colors because basically the model is hallucinating new details, new changes. So I'm not going to talk too much because it's a paper under review, but there are tricks that you can use to solve or at least reduce a lot these kind of hallucinations by adding new information to your model and learn a velocity flow that is dependent on how well specific pairs of images are aligned, which allows you to train on bigger dataset because you can include worsely aligned pairs, so images with a larger time difference in our case, but still learning that, yeah, those are badly aligned because they are far apart, but the changes are covering only a part of the images, so they're still useful to train the generative models. And as you can see, we are able, by increasing this alignment score, which is sort of controlling the fidelity of the super resolution, getting results that are closer to the low resolution version with less hallucinated changes compared to the target, compared to the non-aligned velocity flow, which learns to change the colors of the fields here, which is of course incorrect based on what we expected initially. Another inverse problem that's very common in remote sensing is removing noise in images and observations. One example of that is if you do in SAR. I'm not an expert on SAR, but I'm sure that Flora will have plenty of radar illustrations to give you in her keynote. But one thing that you can do with SAR is interferometry, which gives you an estimation of how much the surface that you are observing has moved between two acquisitions. And in this interferometric measurement, you have many components that are added that contribute to the change in the phase. And some of these components can be removed with pre-processing, but one of these components, which is the corruption noise, we cannot really remove it easily, and this results in displacement maps that are very noisy if you don't remove them. So we can remove most of the information, most of the components that are not the surface displacement, but there's still one part, which is the noisy part, and we want to denoise these interferograms. And this is an inverse problem because we don't know the noise, and the noise operator is not something that's analytically invertible. So once again, if you look at the literature, there are many people doing deep in-SAR denoising with different approaches, mostly predictive, trained on supervised simulated data and so on. There's also more recently in-SAR to in-SAR, which try to adapt the noise-to-noise paradigm to SAR denoising. And there are two challenges basically when you do this kind of denoising. The first one is that you don't have a lot of clean ground truth of denoised interferograms unless you do simulation. And the other thing that's bothering at least me, it's the fact that when you use the standard regression architecture to do denoising, well, it's fine when you're working with images, but when you're working with phase is an angle between 0 and 2 pi. And if you train with standard regression approaches, you can generate noise estimates that are outside of these bounds. And this is just mathematically incorrect. And then you have to do some kind of trick to get back into, 0 to pi. And if you just do regression on that, it does work, but it raises questions, of what do you do when you're out of bounds? And the answer to that is that phase, a point in an interferogram is not real. It's not in the Euclidean space. It's on a Riemannian manifold. I know that the word seems anxious, that you might be anxious facing the word Riemannian manifold, but I promise you that it's not that complicated. If you take only one pixel of the interferogram, it's one angle, so it's a point on the complex circle. If you have 2 pixels, you have 2 angles, so it gives you a torus in 3D. And if you have d pixels, it gives you a hypertorus in the d-dimensional space. So what I mean by that is that an interferogram is not a point in the Euclidean space, it's a point on this torus, which is a Riemannian manifold. So you have to predict a noise that's always on this Riemannian manifold, right? And the good news is that we can do it with flow matching. Diffusion models and flow matching models are very strong generative baselines for image denoising. For diffusion models, the link is probably obvious. If you know diffusion models are denoisers by definition. However, the challenging part is that they are denoisers but defined to work in the Euclidean space R of reals. But there's a paper from iClear 2024, which does flow matching on general geometries, including Riemannian manifolds, and including specifically the torus that we are working on. So this is great because this means that we can do flow matching on the torus. This guarantees that we will never generate phase values that are invalid. And this allows us to actually map the noise to the wrapped Gaussian on the torus manifold, and not a Gaussian in the Euclidean space, which would be incorrect once again, because the noise is not Gaussian in the ambient Euclidean space, it's Gaussian on the manifold. So this is a preliminary work that we did on that was published at GDR last year, where what we tried to do was taking a state-of-the-art denoising algorithm, which is called CoffeePL. And CoffeePL is a multi-temporal denoiser. So they need lots and lots of interferograms to obtain clean interferograms. And they need about 40. So if you use Sentinel-1, as they do, basically they need to wait 1.5 years to get clean version of their interferograms, denoised version of their interferograms, because they need to wait several dozens of acquisitions. And we said, okay, can we do the same thing as CoffeePL, but using only a single interferogram? So not multi-temporal, but just bitemporal. And that's exactly what we did. So we introduced INSAR flow, which is basically flow on the torus for INSAR denoising. And we tried to reproduce as a target distribution the denoised interferograms from CoffeePL. But instead of taking all the SAR images that they got, we only take 2 SAR images as an input, with a little bonus compared to the other deep methods, which is that we guarantee the validity of the denoised interferogram, and we guarantee that we won't have any points that are outside the angles. And so if you haven't done any SAR interferometry, this doesn't look like anything to you. If you have, it looks pretty nice. What I want to show you is that the noise level is pretty high. The noisy interferogram is what we have on the left. So if you can distinguish the different levels of phase, well, you have a good eye. And if you look on the right, the denoised version is quite close to the ground truth, which is not an actual ground truth. Okay, it's the reference from CoffeePL, so it's not perfect, but it's quite close. And keep in mind that on the right, they needed to use approximately 40 interferograms compared to our model, which needed only 1 to achieve the similar results. So another line of work that we've been investigating is domain adaptation, which is something that's, once again, very common in Earth observation. Why? Because in Earth observation, you have data that is non-independent and non-stationary. Basically, the Earth is changing, and it's changing fast. Climate change, human constructions, and so on. So when you train a model, your model quickly becomes obsolete when you have a new sensor that's introduced, when you have temporal changes, when you have geographical changes, because you have trained a model on a specific part of the world and you want to apply it on another part, and so on. And adapting an existing model to new data, to a new domain, is what's called domain adaptation. And we focus specifically on unsupervised domain adaptation, which means that we assume that we have labels on the source domain, the domain that was used to train your long cover mapping semantic segmentation model. But we don't have labels on the target domain, which is the domain on which we want to apply this model. So we have to do unsupervised domain adaptation. And one example I will use is SAR to optical adaptation, which is you have a model that's trained to predict long cover mapping, for example, from optical images. But sometimes you have clouds. And because of the clouds, you have to use a SAR image. But your model has not been trained on SAR image, so it's going probably to predict something that's all the same class everywhere because it's completely out of distribution. And the problem with SAR imagery is that you have lots less models that are trained on SAR imagery. And if you just want to use your own model, you might be interested in doing this conversion from SAR to the optical domain. And once again, I'm going to show you 10 times the same trick. You just use flow matching, but you change what are your source and target distribution. Your source distribution are your SAR images that you encode some way in RGB. Your target distribution are your optical images of the same area. And you can train your model to convert from one to the other, so SAR to optical translation. And then you have your segmenter or classifier that's trained on optical data. And when you don't have the optical data because you are facing a huge cloud cover, you can switch back to the SAR observation, translate it into optical, and use exactly the same model to do the prediction, despite your model never having been trained on SAR data, because you're basically converting your SAR data into the optical domain. Of course, the obligatory table with the bold numbers in the right places. I'm not putting that specifically to show off, but I want to show you that some old image translation methods, such as pix-to-pix, which is based on GAN, are still holding up, and they are even holding up a little bit better than some of the newer methods, such as the unpaired neural Schrödinger bridge, whatever. But what's interesting is that just by switching the class of model to flow matching, you get something that's a lot more robust. And that's a lot more robust, not really on the image quality, FID, and LPIPS metrics, but that's a lot more robust on the downstream applications. So it preserves better the semantics compared to GAN-based approaches, which look nice, but as I've shown in the super resolution example, tend to hallucinate some details. And you can read into the paper. It was published at WACV at the beginning of this year. And it works not only for SAR to optical translation, but we also do temporal domain adaptation. For example, if you have images from before and after a flood event, and you don't have the time to retrain your model after the flood event, your segmentation model, because you don't have the time to annotate, you can still use the similar kinds of tricks to learn to adapt your segmenter to automatically do the land cover mapping after the flood event without retraining your predictive model. Many examples, you can show a lot of them in the paper, but basically you can see that the flow Earth observation that we use keeps better the semantic in downstream applications compared to the other models that tend to change the shape of the buildings, for example, and hallucinate some of the details. So they preserve less of the semantics, which is in the end what we want to preserve when we do domain adaptation. We don't care really about the image quality. We care about preserving semantics. The near final thing that I will present is anomaly detection. I've teased it at the beginning, and that's actually the first work that we did on generative models. And that's a really simple trick. Basically, we are taking things from the 80s, from the autoencoder-based anomaly detection literature, which is, okay, I want to do out-of-distribution detection. In Earth observation, I would argue that no image is actually out of distribution, unless you have like a sensor failure or something like that. But no image is fake or out of distribution. We can assume that all the observations that we have are of real areas. So they are real acquisitions of real events. But some of them are extreme. There are very rare cases when you have a catastrophic flood event, wildfires, and so on. These are rare events that are not really well represented in most datasets. And we'd like to detect those as anomalies automatically. And this is a very straightforward task. It's a detection task. So you want to assign to every image a score. such as you can threshold this score and put everything on the right and label it as that's an anomaly, and everything on the left is okay, that's fine. So ideally, we would like to have some way to separate. So this is all the images that are before the flood event, and they have a lower anomaly score compared to the images that are after the flood event, or even being more rigorous, which is we want images that depict something, a part of the area that has been flooded, and give it a score that is lower than a part of the area that has not been flooded. And of course, we don't have labels to do that, so we have to do it unsupervised. And the idea is really, if you take papers of anomaly detection using autoencoders from the 40 years ago, this was the same idea. We just, once again, swap the autoencoders by flow matching. In that paper, I'm lying a little bit because we use diffusion models, which are a special case of flow matching. Flow matching was not as prevalent 2 years ago as it is now. And what we do is that we train our generative models on the dataset that we have of our dataset of images. So we can assume that these are a dataset of images before a catastrophic event. And our intuition is that if we noise those images, so if we project them into the source latent nodes, and that we reconstruct them after, the reconstruction should be better for images that are in the dataset, so that are not exceptional images, and that anomaly images should be reconstructed worse. So the score that we can use is just project into the latent space, go back into the image space using our generative model, and compute the mean squared error between the images. And that's the basic scheme. And you can use that trick with diffusion models, but you can also use that trick with autoencoders. What we show in the paper, which was an Earth Vision paper from 2 years ago, was that flow matching works better in most cases. And if you want to detect some specific anomalies, you might prefer to use different kind of reconstruction metrics than the standard MSE that everyone uses. And that if you use LPIPs, you are going to detect different kinds of anomalies that if you use MSE or Mahalanobis distance, for example. For the few minutes that I have left, I want to sidestep everything that I have said until now and show you that even if we are in the artificial intelligence and pattern recognition for remote sensing, you can do interesting stuff without doing any learning at all, apart from your own learning, but no machine learning, which is non-learning based generation. My point, and maybe you have understood that, is that I don't like generative models for image synthesis very much. I don't really see the point of generating new images that look like nice images, but I still see the point of generating new images. I just think that you don't need deep learning to generate synthetic data. And training models, deep or classical models with synthetic data, it's not a new trick. What I'm saying is not something new. I'm saying we need to go back to basics. More than 10 years ago, flying chairs was solving the problem of it's very hard to annotate optical flow images. So they just put in Blender or Maya, I don't remember. So they just put chairs in the air in a 3D world, and they generated automatically optical flow pairs. So that was 10 years ago. You might know the Carla driving simulator, which is a simulator for autonomous driving. And that's completely virtual. That looks fine, but it's a complete CGI. Or the Clever dataset for reasoning, which was a dataset used to answer VQA questions, such as how many metallic balls are there in the images. And the dataset is generated from Blender. So you could say, okay, sure, Nicolas, I get the point, but it's papers from 10 years ago. So when you're saying it's old, it's not that old. Okay. Alvin was a neural network trained for autonomous driving on simulated road images. Hot topics from 10 years ago, but the paper was published in 1988. So I want to drive it down, no pun intended regarding autonomous driving, but I want to drive this point. Simulating data to train models is not a new idea, but we have to do it properly. And it's easy to say, okay, I'm going to use stable diffusion and whatever to generate my images. But then you don't know what you're generating. You have no control on what you're generating. And in Earth observation, we have ways to generate data, synthetic data that we entirely control based on virtual worlds and computer graphics. And there are some recent works that are pushing towards simulating what you cannot really acquire and label easily. Synthesis is an interesting work that tries to do stereo matching for depth estimation. And it's very hard to get stereo pairs with the heights of the surface synchronized. So they just simulate it using a City Engine, which is a tool from ArcGIS, to do simulation because they have a 3D model and they just put two cameras that are offset and they render the stereo pairs and they automatically have the disparity maps and the depth estimation. Syntheworld does a little bit of the same thing. They use Blender to procedurally generate synthetic images. So they get OpenStreetMap data, they put some nice buildings and so on, and they put textures on it. And well, since they have OpenStreetMap data and they have generated everything inside Blender, they can automatically produce the land cover semantic map alongside the render. And if you combine that with the plethora of physics-based simulator that exists, such as Dart and ProSail that can do radiative transfer simulation to generate multispectral imagery, you could be able to generate physically robust, annotated images for any task that you like. But of course, you have to work a little bit to define the task that you're working on. So a little bit of advertisement. We're going to push in probably a few weeks a new version of the WorldWeaver procedural generation engine that we are working on at IGN, which is an open source Blender plugin that does procedural generation based on either IGN data or OpenStreetMap. And you can use it to automatically generate. So this is an example of we are flooding Saint-Sauveur-sur-Tinée, which is a small town in Alpes-Maritimes. And we can easily produce the labels that go with that because we have entire control of this full world. And we are trying to adapt it now to, so we have flood simulation and we're trying to adapt it to wildfire simulation because floods and wildfires are events for which we don't have a lot of data and lots of annotated data in particular. So I'm going to end the talk, not end you, hopefully, with a few parting words. So my roadmap for remote sensing, and that's my own roadmap. I'm just telling you, like it's my commitment to the community. It's not asking you to adhere to and come work with me. But my roadmap is, I'm trying to not dismiss generative models, especially not dismiss generative models for other stuff than image generation, because there are so much more than I'm going to synthesize a pretty image. And I think that if we focus too much on that image generation part, we're going to forget the theoretical foundations of generative models and lose a lot of opportunity for growth in the research community. I see, however, two roadblocks, and that's like my pledge of hopefully working on that. The first one is that how can we harmonize our data sources? We have very different kinds of data. We have LiDAR, point clouds, We have multispectral data at different resolutions with different sensor characteristics. We have vector data, which is very different than raster. And I say that as someone who has worked on multimodal data fusion before. I don't think that the approaches that we have of having like data fusion architectures with many encoders is scalable. And I believe that a few years ago, and I don't believe it anymore, because when you try to scale to many different sensors or you try to add a new sensor, everything breaks down. You are facing problems with continual learning and so on. So I don't believe in that. And I believe in harmonization in some way, perhaps using implicit models, at least for rasters, because rasters are really, if you pardon my French, pain in the ass to work with, especially at different resolution and different sensor wavelengths. So I don't know, I'm sure there's a way to do it better. And I think implicit models might be this one. And the second is, how can we improve trust in generative models? What I dislike in image generation is image generation when you don't control what you are generating. If we find a way to do image generation by integrating physics, knowledge graph, expect knowledge, and so on, I would be more than fine with the idea of just using stable diffusion to generate images of floods. But right now, I don't have the trust in these data-driven approaches to generate something that actually looks realistic. So to conclude, and that's the only slide that you really need to listen to me anymore. Generative models, very polyvalent tools. You can use them for plenty applications. If you have an inverse problem, think about it. Maybe try putting generating models against it. You can turn them into classifiers. Don't dismiss that. That's not a completely easy task, but there are people that do this kind of stuff. And if you don't have enough data, maybe consider generating your data. That's not easy, but that might be easier to collect the data that you don't have. That's it. Thanks to Georges Lebellier and Emi Okabayashi, especially because those are the PhD students who have done all the work. All the mistakes are mine, but the good work are theirs. And the collaborators, so Héloïse, Arnaud, Thomas, Nicolas, and Charlotte, who are co-authors on the paper. Thanks, of course, to Einer, who has been funding most of my work for the previous years. And if you're looking for a job, we are looking for a research engineer to train big generative models. And we will be looking for postdocs in the coming years. Thanks. Thanks a lot for your time. Thanks for the invitation. Hopefully, we still have time for comments.
Thank you, Nicolas, a lot for the presentation. So we take questions from the room and also online, if that's possible. So if you want to ask a question online, either you can directly type it and see or me will read it, or just ask for the permission, and we will give you your tour. Okay, there is already one question there. Go ahead.
Yeah, the first one is, what's your take on domain adaptation for unsupervised people? Would that be a viable solution?
For unsupervised what? Sorry.
Denoising. So domain, the first domain would be the noiseless, and the second, the noisiness. I'm not sure if that's a viable.
That's kind of what we do. I'm not sure in what part would be a domain adaptation.
So in case we don't have access to the noiseless data, like from the same sensor, so in that case we'll have pairs of noisy images.
Yeah, so you only have noisy images.
Yeah, well, let's say we're seeing images from one sensor and noiseless images from different sensors.
Yeah, this is basically what noise to noise does. In noise to noise, you're learning to map from a noisy image to another. It's somewhere. The citation is somewhere. In noise to noise, you are assuming that because the noise is random and independent between observations, if you are trying to learn, regress from one image at a specific time and to another image at another time, then the only thing that you can learn is the denoise component, because the noise is random, so you cannot learn it. But I wouldn't call that really domain adaptation. It's unsupervised learning with a pretext task.
I have a second question. Would it be fair to say, at least according to results that we have obtained so far, if you compare flow matching versus GANs in terms of hallucination? So, like, generally speaking, you think that flow matching has less hallucinations for most tasks?
Yeah. So from our observations, flow matching results in less hallucination. It does not mean that it doesn't have hallucinations. I don't really like the term hallucination because I think it encompasses different types of errors that GANs or that generative models can make. But if we use the term hallucination for changing the semantic, which is generally what we use it for, but it's not completely exact, because for super resolution, I've said it's an hallucination, but we haven't changed the semantic of the field, or we have changed the semantic of its state, but not the fact that it's a field. But yeah, flow matching is more robust, and I think it boils down to you have less mod collapse in flow matching for theoretical and empirical reason. And the fact that you are averaging across different velocities and you add stochasticity. So there are tricks to do similar thing with GANs to reduce the mod collapse and hallucination by adding noise. But it's baked in for flow matching. So I think that's one of the reasons it works better. Yeah.
So I think probably, and correct me if I'm wrong, one of the main differences between flow matching and GANs would be when you map the latent noise to the output. In flow matching, you have for every output, you have one single noise vector, but for GAN, you have random.
It depends the formulation that you use for flow matching.
Okay.
There's a stochastic component, and in the formulation that I've presented is a little bit simplified because I don't want to make a complete tutorial on flow matching. But for example, if you use bridge matching, in bridge matching, here you have a stochastic part. Here you have a stochastic part and the interpolant is stochastic, because there's a Brownian, the trajectory that you follow is a Brownian noise, a Brownian motion. So the difference is mostly, I would say that the difference is that GANs are an implicit model, because in GANs you implicitly reduce either the Jensen-Shannon or the Wasserstein distance between the distributions, but the disoptimization is implicit. Whereas in flow matching, you have something that's more closely related to elbow and likelihood maximization. So they are more, similarly to variational autoencoders, they are closer to explicit generative models.
Thank you very much.
We have two questions online. I take the first one, then I give you the floor. So the first one is on your perspective, Nicolas, asking if you could elaborate on the method that could be used to harmonize the data with implicit models.
So I'd have to talk about implicit models, but if you know about nerves, which are neural radiance fields, or yeah, I don't know if I have better examples than that. But the idea of implicit models is that you don't work on the raster anymore, but you train models that learn the continuous function from coordinates to radiometric values. And this would, I think, help to get representation of an image. It's not a raster anymore. It's described by its implicit representation. In other words, it's described by the function that maps a coordinate in space and time and wavelength to a specific value in intensity or reflectance. And then you don't work on the rasters anymore, but you work on those functions, which are parametric functions described as multi-layer perceptron, basically. So you work in another feature space, but since all images are described in the same feature space, you would have less trouble of doing data fusion that we have now, because now we are fighting against tensors that have very different shapes, basically.
Thank you. I think it's good. Right.
Thank you for your talk. That was very nice. I was wondering what happens in models or methods like super resolution or even inside flow when you keep repeating the process. Like, is there like a plateau on the process, or how do you measure it, and how do you know when to stop the diffusion?
That's a good question. So there are two answers. The first one is one thing that's a little bit hidden here. So when I say we are doing, for example, 20 inference steps, it's the number of steps of integration that we do. And since we're using the continuous time formulation, where the time t is a continuous value between 0 and 1, that corresponds at the inference how many steps of sampling that we do. But compared, for example, to the discrete diffusion models where there's the Markovian process, you cannot really go further than 1. It's just how you quantize the time. So what we observed is that with flow matching, you rarely need a lot of inference steps. I mean, it depends what a lot is. 20 is not a lot compared to diffusion models where it can be like 500 or 1,000 steps. But I think your question is more, okay, could I take this denoised version and denoise it again?
Yeah.
In that specific case, I think it would fail, or it would do something unexpected. We haven't tried, so that's my intuition, but that's a good question. Because it's been trained assuming that the noise level is very high. So we would, to repeat the process, we would probably need to train it on a larger diversity of noise levels. And I don't think we can just like repeat it and hopefully get something that's better denoised. In denoising and super resolution, there are papers that try to do this kind of thing, where they expect that if you denoise something that's been denoised, the result should be the identity. And you can add that as a regularization on your loss. So if you denoise something that's clean, then the output should be exactly 0.
Yeah. Yeah, I was wondering because maybe I'm not that fond to diffusion models. So I don't know if there are like artifacts or things that may arise, like, I don't know, a constant bias that you can get using like Fourier analysis or a histogram equalization or standard like image processing to catch artifacts that may be avoided without this too many complexity.
We need a short answer, otherwise we can then discuss later.
Yeah, we can discuss later. In diffusion models, you can have this sort of problems of biased outputs. As far as I know, not in flow matching.
Okay.
Thank you a lot. Let's thank again Nicolas.